Hello, good morning or good afternoon, depending on where you're joining us from, and welcome to today's webinar. My name is Chance Millett-Bangs from the Business Review, and I will be your host. It is our pleasure to have NEC Energy Solutions with us today, who will be discussing using controls to optimize grid energy storage operating costs. Today's guest speakers are Roger Lynn, Director of Product Marketing, and Craig Rutfield, the Vice President of Software Engineering. I'd like to welcome you to our webinar platform on 24. This webinar is browser-based, so if you disconnect, please click the link you received via email to rejoin the session. All of the icons along the bottom of your screen are the interactive widgets that we have on offer today, so please interact with them all throughout the session. You can ask any questions that you have by using the Q&A widget, which is also the questions box in the top left-hand corner of your screen. We will aim to allocate around 10 to 15 minutes at the end of the session to address any questions or thoughts that you may have. Your view is completely customizable, so feel free to move and resize any of the windows in front of you as we progress through the session. Please use the Help widget if you experience any technical difficulties or require any more assistance. So, without further ado, please allow me to welcome Roger. Roger, over to you.
Thanks, Chance. Good morning or good afternoon, everybody. Thanks for joining us on this webinar where we'll discuss controls being used to optimize grid energy storage operating costs and also cover a few items on considerations that should be made when designing energy storage systems and controls. So first, a little bit about us. We are part of NEC Corporation of Japan, which is a large multinational diversified conglomerate focused on the IT space, doing work in smart metering, software, telecom, and IT. Recently, we've been acquired by NEC Corporation. We were formerly part of a company called A123 Systems, which is focused on advanced lithium-ion batteries. As today, part of NEC, we are known as NEC Energy Solutions, and we focus on developing and manufacturing advanced batteries for the electric grid, for backup power, and for replacing lead-acid batteries. We're an industry leader in system integration, focusing on high performance, efficient, safe, and reliable battery systems. And today we'll focus primarily on the large grid-scale energy storage systems used to increase the reliability, efficiency, and intelligence to create a smarter grid. Energy storage can be used for the grid in almost every location, ranging from generation to transmission through distribution, and even on the load side of the meters. We'll be talking a little bit about some of the applications today in frequency regulation and frequency response, but energy storage can also be used to perform applications such as voltage support, transmission distribution, upgrade deferral, or provide better integration of renewable generation, providing benefits throughout the electricity supply chain. So let's get into the meat of the presentation, designing energy storage for the grid. The basics are these three questions. What will it do? How does it provide benefits? And what is the business model? In other words, what is the application will perform? What job will it do? Maybe the job is simply charging up at off-peak times and discharging and selling the energy during on-peak times. Or the job may be more complex, such as providing balancing services to the grid in the form of frequency regulation or frequency response, primary or secondary reserve. Ultimately, the storage system will have a primary job to do and will be compensated for providing some form of benefit to a stakeholder on the grid for hopefully a revenue-generating or cost-saving purpose. Deciding on whether or not to invest in a grid energy storage project depends strongly on the business model being considered. Payments, the costs, the time, and of course, the variability of the business model and the risk posed to investor and the owner of the storage project. And as an energy storage manufacturer and designer and a controls designer, it's our job to make sure that these systems can provide the least amount of risk to their owners to provide the best payback. So let's get into one of the jobs that energy storage can do. And what we'll use today as an example is an application or job called frequency regulation. So we'll get into a little bit about what frequency regulation is, what energy storage can do to provide benefits to this job above and beyond existing forms of resources that are on the grid today, and then ultimately how controls will impact the performance and the overall operating costs of an energy storage system that is providing this job to the grid. So in a nutshell, frequency regulation is the positive control of grid frequency by the system operator. It's a critical tool to allow the grid frequency to remain at a set point. Here in North America, that set point is 60 hertz. And typically the system operator has many resources to try and balance that frequency, to try and keep that frequency at 60 hertz in the face of rapidly changing demands, loads, lights that you might turn on and off, or other resources on the grid consuming electricity, as well as the changes in the generator side of electricity. So it's constantly trying to balance or match generation and load to keep frequency at 60 hertz. This tool, frequency regulation, is used to give that system operator the ability to actively manage the frequency by changing resources in its frequency regulation fleet to help match the variations in load. Typically today, the grid system operator commands resources in the frequency regulation fleet to ramp up and down to directly control grid frequency. These resources can be either generators or loads, so they do send signals out to both types of resources. Issues with this typical solution are that generators specifically must be operating at less than full output and more than minimum output to provide this resource. In other words, if a generator is to ramp up and down to match frequency, it needs to be operating at lower than its full optimal or most efficient set point. So if a generator has to increase output in case of a regulation up signal or decrease output in case of regulation down signal, that generator must be operating at less than its full output. Another issue with using traditional resources is that generators are typically unable to follow the control signal very well. So when the system operator asks for this fleet to move up or down to try and again balance generation with load, typical generators can have a hard time following that signal very, very well. Finally, a comment on the loads. While loads or energy consumers, electricity consumers, can also provide this service, it's inconvenient to shut down appliances whenever the grid operator wants you to. You can imagine that if you are heating your water in your home with electricity, it may be okay to turn water heaters on and off depending on what the situation on the grid is, but something like a television is probably not okay to turn on and off whenever the grid system operator needs you to. So just to elaborate on the issues with traditional frequency regulation resources, I'm showing here a picture of one of the resources that is providing this, the frequency regulation service to the grid. In PJM, which is a regional transmission operator in North America, we're showing the output of a combined cycle turbine in the graph. The three lines on the graph are the assigned regulation, which is in red. This is the committed generator capacity to performing the frequency regulation service for PJM, somewhere around 85, 90 megawatts in this case. The generator gets paid for all 90 megawatts it's committing. It's sort of like a on-call payment to provide this frequency regulation service, even though it's not at that full 90 megawatts of output. The control signal is what the system operator sends to the generator to follow so that it can balance the generation load to keep that frequency at 60 hertz, and it's shown there in green. Now the actual output of the combined cycle generator is shown in blue, and as you can see, it matches it fairly well, but it's not perfect or precise, but generally does a good job of providing the type of power input that the system operator requires to keep that frequency balanced. Now we'll look at a different type of unit. Here's a frequency regulation performance chart for a steam-fired unit. In this case, again, you see that the system is getting paid for 20 megawatts in this case of committed capacity. But when you look at how it follows the frequency regulation control signal, you'll see that it is totally inadequate. It doesn't follow the signal very well at all. In fact, in some cases, it goes in the opposite direction or does the opposite of what the system operator requires. So while today in PJM this performance would disqualify the generator from future participation in this market, many regions around the world still allow slow, inaccurate resources like this one to provide a critical balancing service for grid reliability and still get paid. So what is the value added by energy storage in this application, this job of controlling grid frequency? Well, there are a few inherent characteristics that add value. The first is the fast, precise response of energy storage. Energy storage can provide instant power, matching any signal that's provided with very, very high speed. It can respond in milliseconds to signals provided by a system operator, and also ramp much, much faster than traditional generators can, providing almost vertical power ramping capability, and doing so without increased cost for ramping. Traditional generation does incur higher operational costs due to ramping up and down, whereas energy storage typically does not incur increased cost. Now, we're showing here a chart with the vertical ramping capability of what we call GSS. A side note, GSS is NEC Energy's grid storage solution, which contains energy storage, AC to DC power conversion, and a control system, which we'll talk about a little bit later, called AROS. So what are the values, additional values added by energy storage? Well, with fast responding, precise resources like energy storage, grid operators actually need less of this resource than before to do the same amount of work. So in PJM, we have something called the benefits factor for fast responding resources, like that provided by energy storage. In PJM, that benefits factor is up to 3x. In other words, if a frequency regulation resource of a normal generator puts in 1 megawatt of resource to the system, it's counted as 1 megawatt of resource. However, if a fast responding resource like energy storage is bid in, its 1 megawatt is counted as up to 3 megawatts, which is about 3 times that of slower responding resources. So that means that 1 megawatt of energy storage is worth 3 times that of a traditional generator. So how does it actually work in frequency regulation? Well, as you can see from this chart, energy storage resources can follow that control signal almost perfectly. And in 2012, in PJM, something called FERC Order 755 created the pay for performance frequency regulation market in the United States. And as far as the business model goes, the payment has increased for faster responding, higher accuracy resources like storage. As an example, for the first half of April 2015, revenue for storage was about $35 per megawatt per hour. So in other words, if you have, let's say, a 20 megawatt resource operating in the system, every hour, each megawatt of resource was making $35. So that covers basically what job the energy storage will do, some of the benefits it can provide, and a high-level view of what the business model would be for an energy storage system. The next layer will be, well, how big must it be? What else do you need to do? And will it be enough to do the job? So here's a high-level view of how the GSS, our lithium-ion-based grid storage solution, is designed. We go from basic component cells on the upper left-hand corner, and then integrate those into battery modules, which then go into larger battery racks, and then into large battery subsystems, and finally get put into enclosures or containers and installed on site to form the GSS of the grid energy storage system. A lot of design considerations need to be taken into account to get this system to operate in an efficient manner, to operate in a safe and reliable manner, and we'll talk a little bit about how controls can impact some of those parameters. Now, is energy storage alone enough to do the job? Well, in some cases it isn't. Energy storage solution cannot function as a standalone asset, and integration of the system with all the surrounding assets is required to prevent instability. So the list of interfaces, assets, and protocols will continue to grow. Some of those external interfaces and other assets are listed below. So you can see things like power meters, transformers, HVAC, inverters, of course, fire suppression systems, cameras, switchgear, etc. There's a lot of different resources that go into making an energy storage system a reliable, high-performance asset for the grid. And of course, sizing of energy storage has to be done very, very carefully, configuring and making sure that the amount of energy storage in both power and energy can help optimize the kind of payback you'll get from the energy storage project. Typically here at NEC, we'll do a lot of sophisticated modeling to help determine the right size. Trade-offs, of course, are that more power or more energy result in a higher initial cost. However, can also result in fewer violations, fewer times that energy storage system will not be able to do its job. In other words, making sure that it's always on the job and able to complete the actions required of it for it to get paid or for it to help save on operating costs of the overall system. The trade-offs are made in terms of how much power is installed and how much energy is installed. So finally, we get to running the system, maximizing value and minimizing operational costs. So what's important when we look at those things? Well, the goal, of course, is stated here, maximizing revenue and minimizing costs. Control systems will dictate operational efficiency. So you can imagine that if you operate this thing in the wrong way, you can impact in a negative fashion the cost or the revenue of the project itself. Some of the important factors to consider are availability, round-trip efficiency, and energy storage lifetime. Now, what are each of these parameters? We'll go into a little bit more detail. We'll start with availability. This is a key factor to consider. We'll use the definition of equivalent availability factor, or EAF, which is defined in IEEE Standard 726-2006. Basically says that availability is the fraction of maximum output a resource can achieve if limited only by outages and deratings. So let's consider a 100 megawatt grid energy storage system. By 100 megawatts, we mean it is capable of a maximum output of 100 megawatts, where it is discharging or acting like a generator, or a maximum input of 100 megawatts, where it is charging or acts like a controllable load similar to a demand response resource. Now consider what might impact availability of this energy storage device. Certainly things could break down or simply not work. This is more related to reliability components, MTBF, and other measurements of quality or good system design. However, there's another factor that's unique to energy storage that isn't shared by traditional generators. This is called state of charge. So state of charge, or SOC, is a measure of how full the energy storage is. So you can imagine that if improperly managed, the SOC of a system could end up at 100%. Now, what happens if at that point the system, in order to do this job, this frequency regulation job, for instance, needs to charge? It will simply not be able to perform, and thus will be unavailable. What if the SOC runs down to 0%, it's empty, and then at that moment the frequency of the grid drops down below its target set point of 60 hertz, and the system operator commands the resource, the energy storage resource, to discharge. Again, that energy storage will not be able to do so and be unavailable. Thus, under these conditions, a few things could happen. First, the system will start to maybe rack up violations, of which there may be penalties of a financial nature. So instead of making money, you could be paying money. Second, the customer of the service that your energy storage system is providing may actually elect to disqualify your system entirely as a credible resource. And then you're not just out of the money for that time, you've run out of energy, but maybe for that time onwards, forever. So grid stability especially requires that systems must be able to operate during contingency events to prevent blackouts from occurring, and grid system operators take these resources very seriously. So ultimately, you want high availability. The higher, the better, so that you are more often doing the job and making money as opposed to doing nothing because you're either full or empty. Unavailability due to poor SOC management can be impacted, of course, by the controls, algorithms, and system design. So key takeaways on availability. First, availability is like uptime. How often you're running, how often you're available to do the job. You want higher availability since it increases the time the system is making money. And both system sizing, which is done initially in that modeling exercise where I showed the graph of how much power and how much energy is required, and operating parameters, which is more in situ, can impact availability. Both need to be done carefully and done properly to make sure that the project is a success. The second factor we'll cover is round-trip efficiency, or RTE. This refers to the amount of energy in watt hours that can be returned after it's being stored. It is never 100%. There's always some loss in the storage of energy, of electricity. Storing and returning energy results in some of it being lost in heat or side reactions, and it's not a static parameter either. It can change depending on the operating parameters, of course, storage technology, or the temperature. The RTE percentage impacts operational cost because for every watt hour you put in, you only get a fraction of it back out. That means, on a net basis, all energy storage devices will consume energy. So you can imagine that this energy consumption can be considered a storage fee, and then higher RTE, higher round-trip efficiencies, means that you pay lower storage fees. So key takeaways for RTE: round-trip efficiency is never 100%. You want it to be higher since it will lower your storage fees. And energy storage type, the system design again, and the operating parameters as well. Again, in the in situ type of parameter can all impact the round-trip efficiency and then impact your operating costs. The last one I'll cover is energy storage lifetime. This is sort of a big, complex topic, and it differs depending on the types of technologies being considered or being used. But in general, energy storage devices will wear out over time. So they deliver less power and or store less energy as they are used, as they are charged and discharged. We're typically sized up front to ensure consistent performance over a specific time period to make sure that that energy storage system, that device, will be able to do the job it's being committed to do for the time that's expected for the project itself. Now, when we look at energy storage lifetime, the preferred metric that we like to look at is cost per energy throughput. This is similar to a levelized cost of energy. However, it's applied to energy storage devices in terms of the total cost of the system divided by how much energy actually passes through the energy storage device before it reaches an end-of-life condition. Now, that sounds like it'd be fairly simple to figure out, but this metric can change drastically depending on the end-of-life condition. At what point is this system unable to do its job anymore, right? And that can be different depending on the type of job it's being asked to do, whether it's peak shaving or frequency regulation or T&D deferral. Those are all different jobs with different end-of-life conditions. The metric can change depending on how fast you put the energy through. So if you're putting it at a very fast or high rate, you can wear out the system more quickly. It can change if you run it near full all the time or near empty. If you run it through its full storage capacity all the time or just part of it, that has to do with the state of charge swing or the depth of discharge. How deeply do you discharge that battery? How hot you run the system, and a lot of other parameters. So the metric is, again, not a static one. It does change depending on how you use the system. So to take an example of energy storage lifetime or an analogy, let's assume an automotive analogy. Let's assume a car warranty that allows 1,000 road trips of 18 miles each way. The total miles driven would be 1,000 times 18 miles per trip times 2 trips there and back again for 36,000 miles. To relate that back to energy storage, we can look at the cycles, the number of cycles, as 1,000, the number of trips, the kilowatt hours per cycle, the energy throughput per cycle, which is 18 miles per trip times 2 trips, and then the total energy throughput, which is equivalent to that odometer reading, that 36,000 miles, how many miles you've actually driven on the car, or in energy storage terms, how many kilowatt hours you've put through that energy storage device. So when you look at that odometer, it's kind of like looking at a cycle life graph, which we show side by side here for comparison. So you look at how many miles per year do you need to drive the car. The analogy for energy storage would be how many megawatt hours per year are required to be charged and discharged in the application, in the job that it's being commissioned to do. So we'll do some quick math here. Using that chart, which is for example only, we'll look at the throughput, which is equal to 6,000 cycles times 80%, which is the depth of discharge, how deeply we discharge the battery, times 1 megawatt hour, which is going to be the size of our battery for this example, times 2, which is, again, the charge and discharge there and back again, comes out to 9,600 megawatt hours. If we assume the application requires 960 megawatt hours per year, we'll have 80% nameplate capacity remaining in year 10 as a high-level estimate. To get to this cost per energy throughput metric, or levelized cost of storage, as we call it, LCOS, if we assume the cost is $1 million per megawatt hour of storage, it equates to about 10 cents per kilowatt hour of energy throughput. So that's an interesting metric to use when you're looking at the cost of energy storage and the cost of the degradation over time, its useful life. So key takeaways: battery life depends on a number of factors we discussed before. The impact of a lot of these factors can be minimized if the ESS is properly sized and controlled, and we use cycle life data to calculate lifetime efficiency throughput and compare it to application needs. So to wrap up this section, we've really taken a look at the types of things that energy storage can do. We use frequency regulation as the example. What it takes to properly size and design an energy storage system for the job. And of course, after that, when you're operating it, what do we need to do to make sure it operates at the lowest possible cost, and some of the parameters and some of the factors that impact operational cost. So from there, I'll turn over to Chance again to run our poll question.
Excellent, thank you, Roger. So as Roger just mentioned, it's now time for today's poll question. So if you can pick on the answer most relevant to you and then press submit to log your response. So this question is, if you are planning on doing an energy storage project, when do you need it? Is it within the next 6 months, between 6 months to 1 year from now? Is it 1 to 2 years from now, 2 years out or more, or you do not currently need energy storage? So shortly after this poll question, we're going to have Craig Rutfield, the Vice President of Software Engineering, presenting. So Craig, can you quickly come and say hi and give us a little bit of background about yourself?
Okay, good morning or afternoon. I'm Craig Rutfield. I'm the Vice President of Software, as you said. I've had more than 30 years of software and systems development, of which the last 10 or so have been in the energy and utility sectors. Roles have ranged from being the smart grid architect for the software for a large pilot for National Grid. I was a VP of software engineering at Aclara, which served over 400 different utilities as customers, and is also a very early employee of NEC, which at the time was primarily a demand response service provider.
Okay, perfect. Thank you, Craig. You may now begin your half of the presentation.
Okay. What I'd like to discuss is leveraging off of what Roger just said and get into the impact of these controls in a little bit more technical detail. Whereas, basically, proper algorithm design can strongly impact operating costs, as said, and very often this is a trade-off between long-term and short-term costs. And to describe this, I'd like to use a real-world example, and since we're already talking about the PJM frequency regulation, that's a great one to use. One of the things is that this compensation that one would receive is actually based on one's score, so we'll go through that a little bit. And the provider has the option to maximize their score or just perform well enough to meet their contractual obligations and reduce their long-term costs. So very often it's really the business model that dictates the definition of optimization as opposed to just being able to dictate this is how our system works. So you need that flexibility. As described earlier, the frequency regulation is really balancing the demand and generation to regulate the system. The need for this is increasing actually dramatically because a lot of people don't realize the subtlety that as renewables are being deployed on feeders, that there's unanticipated shifts in loads or available energy, which can affect the frequency. And so PJM has made the frequency regulation control decisions, and they actually are monitoring this, and they send a control signal to the resources and require that they respond accordingly. Now, intuitively, the execution performance would impact the overall frequency regulation performance, and therefore should be accounted for in service participation and compensation. Batteries are a great source because it can respond very quickly and actually works to our advantage here. However, when this was originally done, it did not impact the overall frequency regulation until the FERC issued Order 755, which mandated a pay-for-performance and regulation service. And in October 2012, performance-based frequency regulation was implemented, and basically the objectives changed. It was not just, I can sign up to meet this amount of power or energy, but how well can you do it? And basically, under the new rules, PJM quantitatively evaluates how timely and accurately the power response follows a frequency regulation control. Reg D is what it's often referred to as this input signal that is received from PJM to all its providers, and it's really just an abbreviation of Regulation D as part of the requirements when you read the appendices. The performance score is the key to how you're going to respond, and the biggest change is really the delay, or it's not even a delay, it's actually how quickly you can respond and being able to do this timely and follow the signal as described earlier. As well as, so the three factors of the delay, the accuracy, which is can you follow the shape of the regulation signal, and of course the precision is can you deliver the correct amount of energy when called upon. And what PJM really does is they're comparing this regulation signal and the actual delivered power and calculating a score based on this, and there's a slight lag behind it, but it gives a discount factor in clearing the settlement process. So basically, as we look at this Reg D signal, it's really just a number between +1 and -1, and very often 0. But you can see in the upper right-hand graph how it is varying over time, and it is slightly biased on the charge side, but not big enough to compensate for battery system efficiency loss, which we'll touch upon in a few minutes. In the lower left, you can actually see the 100-hour average of this Reg D signal for a 1-year period, and each of those color changes actually reflects 1 month of time. And if you really start looking at the date and time frames in detail, you'll see some very significant fluctuations in the December and January and February time frame for short periods of time, and those are usually due to large swings due to the cold weather and heating sources being required, and therefore consumption increasing dramatically. So basically, all we can really do is 2 key functions. We can respond to this Reg D fast and accurately. We can respond to the Reg D fast and accurately for good performance score, and we can manipulate this P_ command, or the P command is really the real power command, which is actually coming from the controller to the PCS. All right, so when necessary, we can do this without SOC management. The battery will be depleted due to efficiency loss, as described before. Then it will not be able to follow the Reg D signal correctly any longer, and therefore hurt the performance score. Manipulating the response helps to maintain or recover the SOC, but can result in inaccurate response and therefore imperfect performance score. So there's a balance there. The options to manipulate the response, the only real 2 choices are to adjust the magnitude of that real power command or modify the delay. This, of course, is critical to the performance of the battery life in the long term. So let's actually look at the baseline control case. Okay, we can either discharge or charge, and we can affect how quickly we're going to do those and what is the ramp rate. And if you adjust the manipulating factor based on the SOC, we have the advantage that if there's a high state of charge, then I have the flexibility and we can discharge with a little more emphasis and magnify that a little bit. And then when it's time to charge, maybe I don't need to charge quite as much. So therefore, I'm not putting as much stress on the system. And again, the control algorithms will allow me to satisfy the business requirements while still optimizing the life of the battery and maximizing the total cost of ownership over time. Similarly, when the SOC is low, I will reduce how much I'm discharging so that I can contribute for a longer period of time if it is for a prolonged period of time, and charge quicker when I do have the ability to do so. There are certain conditions that may improve operational costs or revenues. We can prevent a running on empty situation, or at least reduce the probability of it, which prevents a discharge, and vice versa. Preferred SOC ranges to extend the cycle life, and different impedance characteristics will affect the round-trip efficiency. So let's actually look at some simulation results. The results can vary with the physical configuration as well as the cell chemistry and several other variables within the factor. So basically we have multiple lines there where we're actually, under the same circumstances, the variance and the controls will actually oscillate a little bit and vary. However, they're all well within the ideal scoring range of 1 being perfect and trying to get to the attainable goal. Another way to look at this is really look at the performance scores. If you look at the top graph, the green ideally should overlap the blue. The idea is to follow it. Based on the SOC, we can be able to follow as much as we can. But you do see some areas where there's blue and you don't see green, and that's because on the corresponding chart, you can see the SOC is low. So you do occasionally run the risk of missing being able to maintain the ideal perfect performance score, as you can see by the lower graph. However, the key here is that by using the control algorithms and doing this a little bit more intelligently, we can actually reduce the impact and maximize the score and therefore the revenue accordingly. So rather than just doing an ideal on-off, we can actually show the impacts of modifying control where the performance score is improved by using this strategy. And the optimization of the control results in fewer running on empty situations. If you actually look at the graph in the upper right, you can see that the bottom of the graph is less dense because we are reducing the frequency that we're actually going to not have enough SOC to be able to contribute when called upon, and therefore the score is increased dramatically. So finally, I think we have shown that the controls can be used to optimize the energy storage for the grid. This optimization requires knowledge of the application, the parameters, the revenue factors, and operational costs. There is no one-size-fits-all, but you need to be able to provide a flexible, customizable solution to be able to satisfy the optimal business requirements. Frequency regulation, as we've demonstrated, is one of the more interesting jobs out there for energy storage today, since it controls the optimization and can impact both revenue and cost of operation. NEC Energy Solutions has powered the largest fleet of battery-based frequency regulation systems in PJM today, operated by its customer there.
Great.
Okay, so we're going to begin our Q&A session now. So we've had a few questions in from the audience already, but if you do have any more questions that you want to ask, you can send them in using the Q&A widgets or by using the questions box. So let's get through the few that we have already. So our first question is, who is the customer in PJM that is using NEC Energy's equipment?
Thanks, Chance, for the question. This is Roger. I'll take that one. So the customer that's using our equipment in PJM today is AES Corporation. AES, in fact, has purchased the vast majority of energy storage that it uses in its fleets operating around the world today. I think in total, AES has operated about something over 50 megawatts of our energy storage technology in the PJM region alone. And so they are the ones that have deployed our systems in the field. They've been operating since 2008 in total. We've actually got a couple sites down in South America as well, but the ones in PJM in North America have been in operation since about 2010, 2011.
Okay, excellent. Thank you very much, Roger. So I'm going to move on to our next question now, which is how can controls impact operational costs due to round-trip efficiency? Isn't this an inherent characteristic of the storage technology?
Okay, I'll take that one. Yes, there's several factors which affect costs, and this includes the cost of storage, which may be wear and tear, as well as systems costs, such as the operating expenses and replacing components over time. However, the greater efficiency can reduce the cost per kilowatt hour dramatically. And even though there are different variables there's no doubt that the efficiency will allow you to do that. It's particularly valuable if somebody's using the time of use pricing, because then you can intentionally charge when costs are low, and therefore, yes, it is inherent characteristic of the storage technology, but if you use the control algorithms and are aware of what the pricing are, you can optimize it even more and reduce the costs by a larger amount.
Mm-hmm. And there's also other aspects of efficiency that are not just related to the storage technology itself. It's true that efficiencies are inherent to each technology, lithium-ion versus a flow battery versus sodium-sulfur. They all have different inherent round-trip efficiencies under similar charge and discharge conditions. However, efficiencies can also be impacted by parasitic losses, parasitic loads on the system that are in operation just to keep that system within its parameters of temperature, of state of charge, of communications monitoring, being able to talk to the operator of the system itself. And so smart controls will minimize those parasitic losses, only use the cooling when absolutely necessary, not have extra communications or other electronics hardware operating that will be adding to the parasitic loads and thus reducing the round-trip efficiencies, especially if the system's not running. So the system is sitting idle and there's no point in it doing any of these extra tasks. The control system should be able to shut things down and keep things in idle mode to minimize that parasitic energy loss.
Okay, perfect. Thank you both for your response to that question. Our next question is, how does one make the trade-off between performance and energy storage life? What is perhaps most important to consider?
Yeah, that's a great question. I would say that in looking at energy storage lifetime versus the control algorithms that are dispatching it, that are using it, ultimately one has to make a decision between doing that job to either avoid costs, save on operational costs of a system, or make revenue, make money, and get paid for that job, and then look at what the cost on cycling throughput or lifetime degradation would be. That requires a pretty intimate knowledge of the energy storage technologies that are being used, and that kind of knowledge, that kind of information can really only be had through extensive testing of the energy storage technology itself, understanding what the characteristics are for its lifetime, how it responds to different types of charge or discharge cycles, how the battery will degrade under those conditions, under different conditions, and then being able to make a predictive guess as to how much damage is incurred for doing that particular job, that particular event. Maybe you're being asked to discharge for a minute or two. Maybe you're being asked to discharge in a very intermittent mode, up and down, charging versus discharging in a rapidly fluctuating fashion. Those can have different impacts on the lifetime of the storage device itself. And so the software algorithms can do a lot for you, but it can only do as much as it understands how to make decisions. And that does come from intimate knowledge of the energy storage technologies. So at NEC, we spent a lot of time characterizing the energy storage devices that are used in our systems. The lithium-ion that's used today has been tested under a huge variety of different conditions, so we understand very, very well how these systems respond, and we bake some of that into the control algorithms. And so it's a tricky thing to do. It's not a precise science, but it can be done and can be optimized.
Excellent. Thank you very much, Roger. So I'm just going to move on quickly to our next question, and it just asks, is it possible for EES technologies to participate in other markets than frequency regulation at the same time?
Yeah, that's a great question. So the question is about stacking of applications, and this is brought up very frequently in all the discussions that are being held at stakeholder meetings with the system operators, the utilities, etc. So the question is, can you do two things at once? And the answer is, yes, you probably can do two things at once. However, the real core of the question is, can you get paid twice in the same hour for doing two things at once? Today, there aren't many, if any, that I know of, situations where you can get paid twice in the same hour for doing two different jobs. But if you look at something like frequency regulation, and perhaps maybe in that situation you also have a peak capacity issue at certain times of the year, you could do peaking capacity, so replacing a peaker plant, for instance, by discharging at peak parts of the day. Here in the States, typically summer load is the worst because of the air conditioning load on the system, and it's usually worse in the afternoon. So maybe you're doing a peak capacity job between the hours of, let's say, 2 p.m. and 6 p.m. The rest of the time you're doing frequency regulation. You could get paid for both of those, but it's unlikely you get paid for frequency regulation and peaking capacity at the same time between those hours of 2 p.m. and 6 p.m. While you could potentially superimpose both signals on top of each other, there will be a little bit of headroom. Again, that gets into the whole issue of, if a generator is providing frequency regulation, it has to pull maximum output, right? And so you may have to do that same thing with the energy storage device, and thus maybe not get the full payment that you could get because you're trying to do two things at once. But it's something that's being discussed at the stakeholder level in many, many places. Hopefully there will be ways to realize the benefits that storage can bring for doing a few things or being able to do many things, some of them simultaneously and some of them in a more of a partitioning method where you do some things 1 hour, do some things the other hour. And controls can help in maybe deciding how you can do one job versus the next. So for every hour of every day, perhaps there may be an option of things that you could elect to do, and then depending on what the payment is, if we have a real-time market that allows for that kind of information to be passed on to operators of resources that are fast responding like energy storage, the control system could then maybe differentiate between, well, I have job A, B, or C, and they all pay different amounts, but then they also incur different amounts of cost. For me as an owner, my control system would have to take into account the revenue potential, the cost of doing that job, and then make a decision. Do I do A? Do I do B? Do I do C? Or maybe I do nothing and I just wait. So it's a very interesting question.
Okay, excellent. Thank you once again, Roger. I'm just going to take this opportunity to address the audience quickly. I just want to talk to you about the purple Contact Us widget that we have on offer today. So this is a way for you to email both of our speakers today directly without leaving the platform. So if you wish to communicate with Roger and Craig after the session, you can utilize the purple Contact Us widget to start this off. Okay, so moving back to our questions now. Our next one asks, what is the size in megawatts of the frequency regulation market on the PJM?
Total PJM market size for frequency regulation today is somewhere in the order of 700 megawatts. That's how much PJM requires to balance their grid, which is, depending on the load, can be up to 100 some odd gigawatts of load that needs to be managed, and of course generation to match it. For energy storage, since there is something called a benefits factor in the frequency regulation market, energy storage is typically cleared at 3 times the rate of traditional resources. So as PJM looks to each hour of every day, make sure that there's 700 megawatts of some resource out there that it can ramp up and down, at its command using its control signal. It'll clear energy storage at 3 times the rate of traditional generation like a coal-fired plant or a gas-fired plant. That benefits factor does decrease over time. So as more fast resources get into the market, that benefits factor goes down starting at 3 and drops down to 2 and eventually goes to 1. So at some point, as you're clearing these resources in the market, as you're trying to collect them all up, you stop counting energy storage as 3x, you start counting as 2.5x, down to 2x, and eventually to 1x. In total, I would say today, PJM frequency market is maybe in the 300 megawatt size in sort of nameplate rating. And that takes into account the benefits factor and the fact that in PJM you need both fast and slow responding resources to ensure that the system is balanced at all times.
Okay, excellent. Thank you very much. Okay, so I'm just going to ask a question here that's maybe a little bit off topic to the direct presentation. It just asks, what are the latest developments in terms of battery technology? So would you both like to sort of weigh in on that question?
Yeah, I can take a first cut at it, and then maybe Craig, you can follow up. But so battery technology is constantly being developed. We focus on lithium-ion batteries here at NEC because of the prevalence of the technology, the maturity. It's being used for lots of different applications. The latest of which is this grid energy storage application. We have seen it, of course, we're all familiar with it in all of our smart devices, the things we carry around with us to communicate and to stay in touch, etc. But it's been used more and more in automotive world to power things like electric vehicles or hybrid electric vehicles. It's also being used in start-stop vehicles. And then grid energy storage has made probably the most of lithium-ion as the third big application. And so because of that diversity, we favor lithium-ion because it has a lot of characteristics that make it well suited for the types of applications that currently are profitable in the utility markets today. However, for the future, we're looking at expanding beyond lithium-ion to see what kind of technologies we might use to attack some of the very long duration applications. So if you look at sort of the paradigm of energy storage, you have a power capability. Is it able to do 1 megawatt, 2 megawatts, 3 megawatts, and then the energy storage duration will do 1 megawatt for 1 hour, for 2 hours, 3 hours, or 4 hours. As we look beyond 4 hours of energy storage, we start to see that lithium-ion starts to get maybe too costly for the amount of megawatts it can provide at 4 hours or 6 hours or 8 hours of energy storage duration. And so there we're looking forward into other more advanced technologies. So we've looked at flow battery technologies, which are becoming more mature and more prevalent on the grid today. We're looking at variants of battery technologies that look at metal air technologies. We've looked at some of the molten sodium type batteries as well. And so as you look at the universe of energy storage technologies, you'll find that no single technology will fit every application, and you'll have to find the right one for the job. And so as we're system integrators, NEC is focused on finding that right combination of energy storage technologies to flesh out its product portfolio so it can effectively address all of the different jobs that energy storage can do. And as these jobs start to become more economic, start to make more economic sense over time, we'll have the right technology for the job.
So if I can add to that, once you select the battery technology and the cell chemistry, then everything layered on top of that, from the layout of the cells to the batteries to the racks to balancing across racks and optimizing the state of charge, and also we haven't discussed state of health, SOH, as well. That's all controlled by the software above. And so as system integrators, we are working to optimize the different technologies and cell chemistries for each particular application. And the way you actually do the optimization, for example, of SOC, the ideal points to be able to keep things in will vary a lot with the cell chemistry. So it's not just the battery technology itself, but the entire system that's around it to be able to optimize the life and again, reduce the total cost of ownership in the long run.
Okay, excellent. Thank you both for your responses there. Some interesting thoughts from you both. So I'm just going to move on to our next question now, and it just asks, is the lifespan of an ESS unit affected by the controls required for frequency regulation?
Yes, they definitely are, and that's something we pay a lot of attention to because, in the simplest sense, you can always just charge and discharge very frequently and reduce the lifetime of the battery by really just going through too many duty cycles. Whereas if you take a more intelligent approach, you can still get these performance scores in PJM, but be able to put and have less wear and tear on the battery by ramping up a little slower and ramping down accordingly and still meeting the requirements. So one of the more subtle but very valuable advantages of the control algorithms is to extend the battery life.
Okay, excellent. Thank you very much, Craig. It looks as though that may be all the time that we have for questions today. So if we haven't got round to answering your question, then it will be forwarded on to our speakers today and you will receive a response in due course. So just before I conclude the session, do either of our speakers have any final thoughts that they wish to leave with the audience?
Yeah, thanks, Chance. So I want to take the time now again to thank everybody for joining us for this webinar. We've explored some of the ways that controls can optimize grid energy storage operating cost, some of the parameters that can be controlled by grid energy storage that range from availability, state of charge management, round trip efficiencies, or energy storage lifetime. And know that the energy storage algorithms that are baked into the controls that we developed in our AROS platform are all designed specifically for the applications, the jobs that energy storage device is intended to do. And we've had a lot of experience and success deploying these systems around the world, doing things like frequency regulation we've spent a lot of time talking about today, but also doing things like frequency response, primary reserve in other parts of the world, notably in South America, and also in Europe more and more. And then also in helping to integrate renewable generation like wind or solar in ever greater amounts on the grid today. And so if any of you have more questions or want to learn more about what we do, what we've done already for the grid, we've deployed over 110 megawatts of energy storage to date. Please feel free to contact us at the information provided with this webinar or visit our website at www.neces.com. And again, want to thank you very much for your attention today.
So that just leaves me to thank Roger and Craig for what was a great presentation, and a big thank you to NEC Energy Solutions for sponsoring today's session. To the attendees, you will receive an email shortly telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. Please continue to ask your questions, vote in today's polls, and interact with the widgets as the on-demand platform remains interactive. We look forward to sharing further webinars with you, so please do keep an eye out on the website just mentioned, and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all have a nice day.